We introduce 3D SMoE Splatting, a novel approach that revisits the core regression step in 3D Gaussian splatting to achieve a highly sparse and more efficient representation. Here's a visual preview. Notice how our method preserves fine background details with far fewer Gaussians. Quantitatively, our method excels, offering better quality, faster rendering, and smaller file sizes. What enables this improvement? We rethink the regression step of 3DGS. Traditional blending uses a weighted sum of Gaussians. Our method, in contrast, uses a weighted sum of soft-gated experts. Our pipeline builds on the 3DGS framework, but modifies the regression layer. We begin with structure from motion to estimate sparse point clouds and camera poses. 3D Gaussians are splatted into the 3D scene. These Gaussians are projected onto the 2D image plane using the given camera pose. Then, the regression is used to synthesize views. Our key contribution lies in the regression model used at this stage. We replace the weighted sum of Gaussians regression of 3DGS by the SMoE weighted sum of soft gates regression. Recent advances in 3DGS focus on densification and compression. However, the core regression, weighted sum of Gaussians, has remained unchanged. Standard 3DGS uses a weighted sum of Gaussians, with weights derived from color, opacity, and transmittance. Instead of blending Gaussians using accumulated weights like 3DGS, we normalize each Gaussian, dividing it by the sum of all Gaussians. This normalized form acts as a soft gate. Our regression is then a weighted sum of these soft gates. We now test how many Gaussians are needed to model a sharp edge. With our gating-based regression, just 2 Gaussians are enough for a crisp result. Let's give 3DGS an advantage, doubling its count to 4 Gaussians. Despite the added cost, it still fails to reconstruct a clean edge. Only when 3DGS reaches 6 Gaussians does it start to approach acceptable quality. And it comes at triple the cost in both memory and computational cost. We evaluate our method on well-known 3DGS datasets and compare it with state-of-the-art techniques. We consider 2 regimes: low BPP, under 100,000 Gaussians, high BPP, over 1 million Gaussians. We apply the same compression techniques to our method and baselines for fair comparison. At low BPP, our method surpasses 3DGS and 2DGS in quality and speed. We train 50% faster than 2DGS and render 2 times faster. At high BPP, our method performs on par with 3DGS in quality, but requires 20% less training time and has 30% faster rendering. Now we dive into visual comparisons. We begin with the low BPP regime. Compared to 3DGS, our method achieves better visual fidelity. But more critically, 3DGS suffers from floating Gaussians. Entire parts of the scene vanish behind these artifacts. Our regression avoids this issue entirely, revealing clean, unobstructed detail without brute force Gaussian count. Quantitative results confirm the visual improvement. Next, we compare to 2DGS. Their method, while sparse, fails to capture detail, especially in the background, which collapses into blur. In contrast, our method preserves sharpness and detail even with a slightly larger budget. The small difference in model size makes a big impact. Our method trains 50% faster, renders 2 times faster, and offers much better PSNR. After applying compression, our method still outperforms compressed 3DGS. While the background in 3DGS becomes blurry and less detailed, our method maintains better sharpness and clarity. The quantitative results also highlight that our approach not only performs well before compression, but also integrates seamlessly with existing post-processing techniques. Next, we turn to high bit per pixel comparisons. When comparing 3DGS to our method, a key observation is the presence of floating Gaussians in 3DGS. In contrast, our method naturally avoids these artifacts without any explicit handling. While PSNR is on par, we reduce file size by 20%. Next, we compare compressed 3DGS with our compressed variant. Just like with 3DGS, floating Gaussians remain an issue in 3DGS-C, even after compression. In contrast, our approach inherently eliminates these artifacts while maintaining strong visual quality. 3D SMoE Splatting is a new way to splat, sparse, smart, and powered by gated experts. We achieve excellent results, and a regression strategy can also be used as plug-and-play in other 2DGS or 3DGS related methods. As you have seen, 3D SMoE Splatting doesn't just compete, it redefines the game. By rethinking the core regression step, we achieve sharper visuals, faster rendering, and smaller models. But this isn't just an upgrade. It's a shift in how we think about splatting. From brute force to expert choice. From blending everything to selectively gating the right details. from more Gaussians to better ones.